But way out there in space, there's huge clouds of dust and gas. And if one of those clouds of dust and gas is massive enough, its own gravity causes it to start to collapse. So it falls in on itself, and towards the centre of that cloud, it gets denser and denser, it gets hotter and hotter. And eventually, the particles that the gas and the dust are made of are brought so close together that they start to stick together, they start to fuse. That's the energy source of a star. The star switches on and begins to shine.
Inside every newborn star, hydrogen atoms are fused together to make helium. This process is called fusion, and it creates the energy that powers every star. What happens to a star during the rest of its life depends on how massive it is at its birth.
A star like the Sun is in a delicate balance between gravity, which wants to make the star collapse in on itself, and the pressure that pushes outwards that comes from the energy that's been produced in these fusion reactions happening at its core. However, at some point in the future, the hydrogen runs out. And at that point, the core of the star will start to collapse in on itself under its own weight. It gets denser, it gets hotter, until a point where you can actually start to use the helium atoms themselves as the fuel for the fusion, pushing helium atoms together and making carbon and oxygen the next heavier elements in the periodic table.
As the star begins to fuse helium, it creates more energy, and that causes the outer layers of the star to expand. One day, our sun will grow so large it will swallow up the inner planets of the solar system, out as far as the Earth. It will become a red giant. For the sun, this will be the beginning of the end.
What happens is, as the outer layers of the star get farther and farther from the middle, the force of gravity that they feel is getting weaker and weaker. And actually, the star loses hold of its outer atmosphere. Its outer atmosphere drifts off out into space. It expands out to become a planetary nebula. And they're some of the most beautiful objects in the universe.
Once the outer layers have drifted away, all that is left of the star is its core.
A white dwarf star is the dead remnant core of a star like the Sun at the end of its life. What's left behind is something that might weigh as much as half the mass of the Sun, but it's only about the size of the Earth. So it's an incredibly dense object, it's dead, there's no nuclear fusion going on in it anymore, it's incredibly hot, but then over millions of years it will gradually cool down to become a black dwarf.
Some stars, however, are much more massive than the Sun, and they lead very different lives. They are able to fuse heavier and heavier elements inside their core. The star gets bigger and bigger. Some grow up to 1,000 times the size of our Sun, until it has fused elements all the way up to iron.
And once we've formed an iron core, there's no more energy can be got from fusion. That core collapses. The rest of the star starts to collapse in after it, but then it bounces off. There's a huge shock wave, and in just a second, bang! The outer parts of the star are blasted off into space in a huge supernova explosion. These supernova explosions are so powerful that when one of these stars explodes, it can actually outshine the whole galaxy of which it's part, a galaxy of maybe 100,000 million stars.
For these supergiant stars, all that is left is the super-dense core, known as a neutron star, an object that can have a mass greater than our Sun, but be less than 20 kilometers across. But for the most massive stars of all, we think when the core collapses, the gravity is so strong, it becomes a black hole, from which not even light can escape.
So stars are actually the places in the universe where the elements are created.
After the Big Bang, our universe contained only hydrogen and helium. All the other heavier elements were therefore fused inside stars.
The amazing thing is that virtually everything you see around you was made inside a star billions of years ago, before the Sun and the planets were formed. And when that star died and blasted its guts out into space, that formed the raw materials from which our Sun, the planet Earth, and indeed ourselves were made. And actually, I think that ultimately that's one of the major reasons why I think understanding stars is crucial, because it's actually telling us where we came from.
It's not a clone of Earth. But for the first time, planet hunters think they have evidence of a planet about Earth's size that could have liquid water in orbit around another star. Kepler 186f, the outermost world of a 5-planet system, orbits about 3 times closer to its star than Earth is to the Sun. But that star, Kepler 186, is an M dwarf. It's much cooler than our bright Sun. So, scientists of the SETI Institute at NASA Ames Research Center are confident the new world is in the so-called habitable zone of that star. M dwarfs live very long lives, plenty of time for possible life forms to develop and evolve. M dwarfs also tend to flare more than our Sun, but Kepler 186f is thought to be at a safe distance, and the enhanced radiation might possibly speed the mutation rate of organisms, driving nature's evolutionary tinkering there. This planet, discovered using the transit method by the highly successful Kepler mission, is only about 10% larger in diameter than our planet. So it's thought to be a dense and rocky world, like Venus, Earth, and Mars in our own solar system, which hold atmospheres made of gases released by their own volcanoes and water collected from impacting comets. Planets larger than about 1.5 times Earth's diameter begin to draw atmospheres made of hydrogen and helium, like our Neptune and Uranus. And they keep on puffing up, like our Saturn and Jupiter, and even growing much, much larger into what scientists call super-Jupiters. Gas giants are not conducive to life on their surfaces, if they even have solid surfaces. No one knows at this point what the surface of Kepler 186 is really like. If there is water, it could be frozen, because the planet is pretty far out in the star's habitable zone. But being larger than Earth, it might hold a thicker atmosphere, which could keep the temperature up and the water liquid. As for the possibility of life on Kepler 186, that may have to wait for a future generation of telescopes. The planet is about 490 light-years away. We'd likely need a powerful space-based instrument to detect oxygen, ozone, or methane in its atmosphere. Seeing those gases in abundance would likely be the products of biology, life as we know it. Of course, there is a small, but not unrealistic chance that intelligent life could have evolved there, and an even smaller, but still valid possibility that they are, or were, transmitting radio signals now detectable by our technology. Specifically, the SETI Institute's Allen Telescope Array, which has, in fact, begun making wide frequency range sweeps of that part of the sky. For Space.com, I'm Dave Brody. And if you have a question about all this, tweet me at DavidSkyBrody.
Space.com.